In this video, I'm going to start talking about NMR spectroscopy, so that's nuclear magnetic resonance spectroscopy. And in this video, I'll be talking about sort of the physics of what's actually going on inside the NMR instrument. And so this is going to be a very physics-heavy video. So a nucleus with an odd atomic number or odd mass number has a nuclear spin that can be observed by NMR spectrometer. So the reason it has to be odd is because, say, we have two protons here in our nucleus. One will be spin up, the other spin down, and so they cancel each other out, and we get zero spin. Whereas, say, we have just a proton here, which is what we'll be mostly talking about in this video, then there is nothing else to cancel it out, and so it has a net spin in the nucleus. And so that's why we need it to be just a single proton, as in HNMR, or a odd number of protons and neutrons in our nucleus in order to get something like the carbon-13 NMR, which is also why you'll often see things like deuterated water used when you are trying to do NMR in something that is water soluble, because then you get the proton, which has the spin up, and the neutron, which will have the opposite spin, and so the deuterated water will not show up in the NMR. So a proton is just a single proton, obviously, which has a spin. This can be modeled as behaving like a spinning and therefore moving positive electric charge. So a moving electric charge generates magnetic fields, which we symbolize with this B here. And so we have this right here, which is our proton, which we can model as a current going through a wire here. And that current will then generate a magnetic field. And so we can model this as being sort of like a small bar magnet like this. And so when a bar magnet is placed in the field of a larger magnet, it will twist to align itself with the field of the larger magnet. And so we see right here, we turn on this magnetic field and this bar magnet will twist. And most of them will twist to get what's called the alpha spin, which is lower energy and more stable. But quantum mechanics, we can get a beta spin, which is actually aligned against the magnetic field. And so that has a higher energy and is less stable. And so the same will occur when a proton is placed in an external magnetic field. The magnetic moment aligns with or against the field. When it's aligned with, it's called an alpha spin. When it's aligned against, it's called a beta spin. So in the absence of this B sub naught, which is our magnetic field, the proton magnetic moments have random arrangements, and then when we turn it on, they will align either with or against the magnetic field. So here they're randomly aligned before we turn on the magnetic field. The magnetic fields turn on. These will then align. And what we see is that most of them will align with the magnetic field, and then fewer of them will align against the magnetic field. And the different states have a difference in energy. So we have the alpha state here, which is aligned with it, the beta state, which is aligned against it, and we have this difference in energy here that is based on the gyromagnetic ratio, the Planck constant, and the strength of our magnetic field. And so the gyromagnetic ratio is going to be based on the atom that's actually present. And so when we're talking about a proton, which is just a hydrogen nucleus, then we get this for our gyromagnetic ratio. And so if we look at nuclear magnetic resonance, we have nuclear magnetic moments, which have quantum properties that allow it to only take up certain allowed angles in the applied magnetic field. And so we can think of it like this. So we can only take up these certain angles with respect to our magnetic field like this because of these angular momenta here. So the magnetic moments have a spin, which means that they have the angular momentum here. And because the nuclear spin moments cannot align perfectly along the magnetic field, because that would violate the Heisenberg uncertainty principle, there is therefore a torque on it. And so we can think of it this way. We have our magnetic moment here. We are applying this magnetic field. And so there is this angular momentum here when that gives us a torque. And when we have this torque plus angular momentum, we get what is called a precession, which we denote by this P here. That means that this angular momentum and this torque is causing our magnetic moment to spin around this magnetic field here. So it's constantly spinning around in what is called the Larmor precession. And in my quantum mechanics playlist, I've made videos about the Larmor precession if you were interested in that. But for now, just know that we have this magnetic moment. We turn on this magnetic field B sub naught here, and that causes a precession around the magnetic field. So the frequency of this precession is this omega sub naught right here, and it's based on the magnetogyric ratio, which we've already discussed, and the strength of this magnetic field, where this gamma here, our magnetogyric ratio, is going to be different for different nuclei. And so this results in a wide range of frequencies where NMR signals can be detected. So many isotopes have a spin half with two energy levels. These are basically just the same energy levels as our alpha and beta, but we're now talking about the population energy levels. And so what I mean by that is we have multiple of these types of magnetic moments here, and most of them will be in the ground state here, and then some of them will be in this upper state here, which correspond to our alpha and our beta. And what that does is our bulk equilibrium will therefore have a magnetic moment. That's because most of them are oriented upward and fewer of them are oriented downward. And so we get this bulk magnetization, this bulk magnetic moment for our sample here. And so, as I said, in the real sample, we have a large number of them, and this M sub Z here is going to be the upper minus the lower magnetic moments here. And so that gives us a bulk magnetic moment. So these spin half nuclei interacting with the applied field here have the two possible energy states, as I said, which we're calling the N sub U for the upper and N sub G for the ground state. And these will have this ratio, which is the Boltzmann equation. So this tells us about the energy of that system. So a constant, strong, homogeneous B sub naught field, so usually between 2 and 23 Tesla, generated by a current in a solenoidal coil, is applied to the sample. So we have this solenoid right here. This will generate this B sub naught magnetic field right here. So in addition to this B sub naught field, we need a B sub 1 field to induce a phase coherence in the XY plane. So we have this RF coil here, this radio frequency coil, and this can induce a perpendicular magnetic field to our sample. And so this induces a magnetic moment in the XY plane. And so that will look like this. So we have our sample right here. So these are all incoherent. So we have a bulk sample, remember, so they have these magnetic moments, and they will be oriented in these different directions around our magnetic field, our B sub naught, and they will be in random orientations, and so we have no magnetic moment going in the XY plane. But when we turn on that B sub 1, we induce a coherence on them. So they all point in roughly the same direction, and that gives us this magnetic moment perpendicular to this one, and it also weakens this magnetic moment right here. And so the applied radio frequency B1 field is this oscillating sine wave equivalent to two rotating fields going in opposite directions, but only one of them is rotating in the right direction to induce phase coherence. Because remember, these are all going to be rotating, and they're rotating in this direction. So only the B sub 1 that is also rotating in that direction will induce a coherence to it. So at equilibrium, our mu sub n are aligned along the field and sum against with a net magnetization of m sub z here, which is greater than 0, since more are aligned along the magnetic field. But as I said, we have an m sub xy of 0. When we turn on this B sub 1, we then get a magnetic moment in the XY plane, so that is no longer equal to 0. It's induced by this B sub 1. And so to understand the effect of this, we can go into a new reference frame. And so what we have is, remember, our B sub 1 is rotating, so it looks like this. And so what we can do is then just change into, this should be the Y prime and X prime right here. And so now we just look at the rotation of our magnetic moment, essentially. So we turn on this B1 right here, and we induce a rotation on this magnetic moment here. And so it's actually a little more complicated than what I'm showing here, because you do things with like 90-degree phase flips, but for our purposes here, we can think about it in this sort of simplified way, where we have the alpha state, which is, remember, pointed along our B sub naught here, but then when we turn on this B sub 1 for a certain amount of time, it will be enough time for us to actually flip the magnetic moment for it into the beta state right here. And that time that's needed to do that 180-degree flip is going to be important, because that tells us how long we need to pulse our B sub 1. And so remember, we have the different energy states here, so the differences in energy between the alpha and beta, and that's going to be based on the strength of our B sub naught, which is our static magnetic field strength. And so based on that static magnetic field strength, it's going to be a different amount of energy that is needed to flip this from the alpha spin state to the beta spin state. And so if we see this right here, so we have the strength of our applied magnetic field, the difference in energy is going to be different based on the chemical or electrical environment of our proton. And that's going to become important here when we are looking at the protons in different chemical environments. So something that is less affected by the magnetic field is going to come to this same difference in energy given by these dotted lines here and here, is going to have to require a stronger magnetic field strength to get that same difference in energy there than something that is more affected by the magnetic field. And so something that's more affected by it is something that is less shielded, which I will talk about more here in a little bit. Something that's less affected by it will be more shielded, and that will be based on the chemical or electrical environment that that proton is actually in. So the energy difference between the alpha and beta spin is quite small, around 10 to the negative 5 kilocalories per mole. So when a proton interacts with the RF pulse, which is our B sub 1 of the correct frequency, the proton's spin can flip from alpha to beta, as I discussed. So when the nucleus is subjected to the right combination of a static magnetic field and RF pulse to flip its spin, it is said to be in resonance. And then we also want to look at the decay of this magnetic moment. So remember, we're inducing this magnetic moment in the XY plane, and we want to look at the decay of it. What I mean by the decay of it is, if we look back up here, so we are inducing this magnetic moment here, this what I call M sub 1 here. I've kind of changed my notation here, and this comes from the fact that I'm using multiple different sources, but we are inducing this XY magnetic moment here. But once we turn off that B sub 1 pulse, we're going to decay back to the equilibrium incoherence here. And so that means our M sub Z will increase in strength, and this M in the XY plane will decrease in strength. And so that is what I mean when I say that we are decaying. And so the decay of this magnetic moment here, which is going to be detected by the NMR instrument. So remember, this is our Larmor precession frequency, which is based on this gamma, which is going to be based on what type of nucleus we're looking at, and the strength of the B sub 1 here. So I'm cutting in here because as I was editing this, I think I wasn't very clear on what I was talking about in the section about to come up in the video. So I was talking about this Larmor precession here, and now I'm using this B sub 1. And so what that means is I'm talking about the Larmor precession. So earlier I was talking about the Larmor precession that was around the B sub naught in the static magnetic field, where this is rotating around in this direction. So what happens is when we use that B sub 1, we generate a magnetic field in this direction. And so that means we get another Larmor precession that is going to spin around that magnetic field. And so we are now spinning around in that direction, around the B1 field. And the reason we want to do that, as we have discussed and will discuss more in this video, is because we want to flip some of these magnetic moments from the alpha spin to the beta spin. And so that is actually what I'm talking about in this part of the video here, where I'm talking about this Larmor precession right here. But anyway, back to the regularly scheduled video. So the amount of time t that it takes for the magnetic moments to flip by 180 degrees, which is pi radians, is dependent on this gamma, which is, as I said, a function of the atoms being measured, and the strength of our B sub 1 pulse here. So this is the time it will actually take to flip it by pi radians here. So the transient signal induced by these spins perturbed by the B sub 1 pulse is called the free induction decay, or FID, and this can be translated into a frequency-dependent spectrum by Fourier transform, even if it arises from many chemical groups, which is important because remember, we're looking at the protons, and they're going to be in a molecule, they're going to be in different chemical or electrical environments. And so we are looking at many chemical groups at the same time. And so they will have their own Larmor precessions and therefore their own decay rates. And these decay rates here have to do with the decay of the M in the XY plane, which is the T sub 2 here, and the recapitulation of our M sub Z. But the T sub 2 you can think of as just the decay of this signal here. So we do a B sub 1 pulse, and this causes a Larmor precession that can actually be seen. So it's a Larmor precession of that M in the XY plane. But as that decays back into equilibrium, that M sub XY is going to decay back to 0. And so that's what the decay of this signal right here is telling us. And so we can have something that looks like this, which is very coherent, and so this tells us that we just have one signal after we do a Fourier transform on it. Something a little more complicated like this, we get these two signals. Something that looks a lot more complicated like this, which is what we will see in an actual sample, since there are multiple protons in different chemical or electrical environments. And so when we do the Fourier transform on that, we get these multiple signals like this. And so this is what an NMR spectrum will usually look like. And so remember, like I said, we have this T sub 2 here, which is telling us about the decay of this right here, of our free induction decay. And so I'm not going to go into too much of what the T sub 1 and T sub 2 mean, because that will bring us into things like the nuclear Overhauser effect and things that are kind of beyond the scope of this video. But the thing I wanted to point out is just that the T sub 2 is going to tell us about the width of these peaks. So once we do the Fourier transform, it will tell us about the width of these different peaks here, where it tells us about the area under the peak. So for instance, we see this one here is quite thin, where this is a lot thicker of a width. And so that's what that T sub 2 is telling us about. So to get the resonance frequency of the nu sub naught here for the energy difference delta E of our N sub G and N sub U states, we get this. So this is the energy difference in them. So remember, if we look back up here, we're looking at these different energy differences here, which is a function of the strength of our static magnetic field. And so this will tell us something about the electric environment of our proton, because it will take a different strength of that static magnetic field to get the same energy splitting depending on the chemical or electrical environment of that proton. And so this is going to tell us something about the nu sub naught of the B sub 1 RF pulse that is needed. And so the larger the delta E, the better the resolution that we can actually get. And so if you actually look at these NMR instruments, you'll see them say something like this one is, a 60 megahertz, or this one's a 200 megahertz, or a 600 megahertz instrument. And so that is going to tell you about the resolution that you can get. So the higher these can go, the better the resolution you can get. And so as I've kind of been hinting at quite often, these protons that we're looking at are surrounded by negatively charged electrons. And these negatively charged electrons generate their own small magnetic field, and it will actually oppose the B sub naught that we are using. And what that does is actually shield the nucleus from that static magnetic field. And so the nucleus will actually feel a weaker magnetic field because of that shielding. And we could think of the magnetic field that it feels as the B effective, which is going to be equal to our external magnetic field, that's our B sub naught, minus the induced magnetic field of the electrons that oppose the external magnetic field. So for instance, if we have at 300 megahertz an unshielded naked proton absorbs at 70,459 Gauss. But say we have 1 Gauss of shielding, it will then absorb at 70,458 Gauss. And so it has been shielded by 1 Gauss. And so protons in different chemical environments are shielded by different amounts. So for instance, in methanol, we have the electronegative oxygen atom, which withdraws some of the electron density from around the hydroxyl proton. And so the hydroxyl proton will be less shielded than, say, the protons on the methyl group right here. And so therefore it will feel more of that external magnetic field. And so we say that the hydroxyl proton is de-shielded in the presence of the electronegative atom. And so different molecules will have these diverse structures which have protons in different chemical environments, which will feel different amounts of de-shielding. And so what that means is that the number of different absorptions, called the signals or peaks, implies how many different types of protons are present. And so in later videos, we can look at these different absorptions to tell us what types of equivalent protons we can get. So I say equivalent because what I mean by that is, say we have something that looks like this, and so this has H3 and this has H3. Even though these are bound to different carbons, they are equivalent protons because they are in the exact same chemical environment. They are bound to a carbon, which is bound to an oxygen, and so they are in the same chemical environment. Whereas, say, something like H3C, CH2 bound to O, bound to CH3, while these hydrogens are bound to a carbon, and these 3 hydrogens are bound to a carbon, they are in different chemical environments because these ones here are closer to an oxygen than these ones. So these hydrogens here are called equivalent, while these ones are not equivalent. Equivalent ones will all show up at the same peak. Non-equivalent ones will have their own peaks. But the amount of shielding shown at these absorptions implies the electronic structure of the molecule close to each proton. So these ones are in a different electronic environment than these ones. And so as I said, they show up at different points in our spectra. But the intensities of these signals, so the height of the peaks, tell us about how many protons are in those chemical environments. So for instance, on this one here, this will have a large peak because there are 6 protons in that chemical environment, where if we look at this molecule right here, these protons are in a different chemical environment than these ones, and so the peaks for those will be shorter, but they should be equal in area under the curve since there are 3 here and 3 here. And so that tells us information about how many protons in that equivalent chemical environment are actually present. And so we can think about it this way. We have our methanol here. This has 1 proton in this chemical environment, then 3 in this equivalent chemical environment. And so the area under this curve will be, well, we can just say that it's 1, say. Then the area under this curve would be 3 of whatever units we're talking about. So just the area under the curve of this one will be 1 since there are 1 proton there, and under this one will be 3 since there are 3 protons there. And what we see is that this one will show up further to the left on here. Because it is de-shielded, we didn't need as strong of a B sub naught to actually get that to show up. Because remember, the energy difference here is going to be based on the strength of our magnetic field. And so something that is de-shielded is going to be more affected by the magnetic field, and so therefore it will show up right here, and something that is less affected by the magnetic field is something that is more shielded, and so it shows up at a higher magnetic field right there. And so the thing that is de-shielded will show up to the left because it shows up at the weaker magnetic field, where these ones here that are not bound to the highly electronegative oxygen are going to be more shielded, and therefore will require a stronger B sub naught to actually show up in our spectrum here. And so we say that these 3 hydrogens here are more shielded. We say that they are higher field or up field, and they have more protons, so they have a higher intensity. Something else that I'll talk about more in future videos that will become important is that these can actually become split, but that has to do with the chemical environment, and so that has to do with the hydrogens being bound on carbons or other atoms that are close together. But as I said, I will talk more about that in future videos. But anyway, that was everything I wanted to talk about in this video. I hope you found that helpful, and I will see you in the next one.